So I want to look just at a couple, extend what we talked about yesterday, and let's look at a couple weird inequalities that when you graph them, they're not typical, not like the stuff we looked at yesterday. Like, how about this one? What symbol, by the way, is that? That's and. Good. So there's an and symbol. So this is one. Let's get phones away, please. So this is one with the word and. The symbol counts for the word and. So we'll solve these individually. Let's kind of color code these things. So we've got the blue one over here and the red one over here. Okay. Easy to solve, no big deal. What are the two steps in order to solve the blue inequality? Get x by itself. So what would those be again? Two steps in order? Subtract 5 and then divide by 2. Okay, so if we do those two steps, we get 2x is greater than 14, right? And so x is greater than 7. And how about the red one? Two steps in order. Add 6, divide by 4. Okay, so we end up first step, we get 4x is greater than 24, divide by 4, and we get x is greater than 6. Okay, this is a little weird, right? We're used to seeing an and statement where x is greater than one number and less than another number. Hold that thought. Okay, as I was saying, so we're used to seeing and statements that are different than this, right? We're used to seeing and statements where x is greater than some number and less than another number. So it's going to get pinched in between two endpoints, right? This is different. Let's graph this and see what's going on here. It helps to think about the graphs. So we've got on the x-axis, we've got two numbers, 6 and 7, right? So if we graph the blue inequality, we end up with something like this, right? We get x is greater than 7. That looks like that one. If we graph and I'm putting them above everybody see what I'm doing here? I'm putting them above the number line so then we can put our solution on the number line. There's the blue inequality, starts at 7 and moves to the right. The red inequality, x is greater than 6, looks like that. Okay, now from yesterday, for an and statement, how many of the inequalities have to be true for the solution when we graph the solution? Both do, right? So in other words, we want the places where an ant could be walking on the number line and be in both the blue and the red regions, because both of those inequalities would have to be true. Now, what does that look like? Where are both of those true? For what interval? Say it again. Okay, after 7, right, good. They would overlap here. So our solution would look like this, wouldn't it? We would have an open endpoint at 7, right? Because the red is included there, but the blue's not. That's an open endpoint for the blue. The double shaded region would start for values greater than 7. Give me thumbs on that concept. Does that make sense? Okay, so that's our solution, right? Okay, so I mean, probably by graphing it is one way. Once you've graphed it a couple times, though, maybe you can even just think your way through this. If we know that we want the places where both things are true, x is greater than 7 and x is greater than 6, what would the solution have to be? Well, for both of them to be true, x would have to be greater than 7, because if we pick a point, like just to kind of test our reasoning, if we pick a point in between 6 and 7, we could test that out and ask ourselves, like 6.5. Is 6.5 greater than 6? Yeah. Is 6.5 greater than 7? No. Right? So 6.5 should not be part of our solution in that case. Does that make sense? But you can always just graph it too. Just graph them both and look for the overlapping region. Okay? So that's our solution then. We want to find What is the answer? Well, that's it. The solution to this one is x is greater than 7 using interval notation. Oh, not here, I said 7 and wrote 6. X is greater than 7 using interval notation. What would that be? Comma, infinity. Infinity always goes with parenthesis. There you go. Okay, give me 1 to 5. Does that make sense? Okay. All right. How about one like that? We got an or statement this time. So again, let's just make this. We've got a blue inequality and a red inequality, and we'll compare the two. So let's solve the blue one. What are the steps in order to solve the blue one? -6 and divide by 4. So we get 4x is less than or equal to 28. So what? X is what, everybody? Less than or equal to 7. Okay, good. X is less than or equal to 7. Or how about the red one? What are the two steps in order? Add 6 and then divide by, there you go. So add 6 and divide by 3. So we get 3x is greater than or equal to 12. So x is greater than or equal to 4. Okay, so now let's explore this one. If we graph this guy, we've got numbers at 4 and 7. The blue inequality, x is less than or equal to 7, is going to look like a solid endpoint at 7, shading which way? Left to the left, okay. So we got that guy. The red inequality, x is greater than or equal to 4, so closed endpoint at 4, shading to the, okay, now how many of the inequalities must be true to be a part of the solution for an or inequality? How many statements have to be true for a, only one of them does, right? So we're looking at all the places where an ant could walk and be in either the blue or the red region. So where's that going to be? 4 to 7 is where both are true, but we said only one of them has to be true, right? So we want to know, where could the ant be walking and be in either the blue or the red? Anywhere, right? Everybody agree? There's no place where the ant is walking where he's not in at least one of those two regions, blue or red. Make sense? So our solution here then to this one is going to look like the entire number line. So what is that? All real numbers, right? Remind me how I say that with interval notation. Yeah, right. The endpoints of that interval would be negative infinity on the left and positive infinity on the right. So it looks like that. Okay, give me 1 to 5. That all make sense? Okay. Okay, so it just takes a little practice. And then the last thing is just here's a summary just for your notes, right? Summary of all the stuff we talked about, what the graphs of these, these different types of inequalities and compound inequalities look like. And then last issue is just something that's going to be not really that new to you, right? Some new terminology for a concept we've already talked about. So union operator is the U, right? Kind of like an or statement for inequality or for interval notation. That means the union of some stuff. Flip that around and it's like that's the equivalent of the interval notation and statement. That's what we mean for an intersection. Union means everything from all contributors. Intersection means only the parts that overlap. So let's look at a couple quick examples here. So if I've got these intervals from -9 to -5 and from +6 to +9, we want to find the intersection of those two. Well, is there an intersection of those two? Do they intersect? If we color code this, they don't, do they? If we color code this, so that's going to be blue, isn't that one going from there to there. And the red, whoops, that's not red. And the red portion goes from +6 up to +9. There is no intersection, right? So for that one, the answer is the empty set, or no solution, right? Okay, how about this one? The the union of, we did intersection first, didn't we? Yeah. So this is the union of these two intervals, right? -1 to +8. So that looks like this guy. And from 0 to 9. So what's the union of that? Where's, in other words, the combination of all the points included in both of those intervals? What would that look like? Where does it start? 0 with an open endpoint. Okay, because there I can't include 0, right? Because when an ant stands on 0, he's not in the blue or the red region, but everything to the right of 0, he's going to be in the blue region at least. Now he's in both. Okay, what about here? When he gets to 8, he's no longer in blue, but he's still in red, right? So where does it end? 9 with an open endpoint. Agreed? Okay, so then our answer, the union of those two, is going to be the set parenthesis -1, parenthesis with a 9. You know, it's going to be between -1 and 9, not including the endpoints. Okay, make sense? Okay, how about this one? The union, we'll make this guy blue. So -infinity to -1, that looks like this, not including -1. The red one is going to go from -2 to +7, and not including +7. So we want the intersection of those two, right? Intersection symbol. So where's that going to be? What is going to be the part where an ant could be standing in both red and blue? He's included in both sets. Where's it starting, Alexandria? -2. Okay, and that's solid or close or open? Solid, good. Okay, we get a solid endpoint there, and where does it end? -1, solid or open? Open, yeah, makes sense. That's the only place where those two intersect. I want to make up one more example. I'm just thinking of a couple problems that I know are on the homework. Let's do one more. So I've got the red set. Let's do the red set. 1, 2, 3, 4, 5. And we want to do the intersection of that set with the blue set. 2, 4, 6, 8, 10. What's the intersection of those two sets? Now this time I've got sets of just discrete little values, elements. So this one's not really you could do it on a number line, they'd just be points, but we can just look at the values. If it's an intersection, what's that mean? No, intersection doesn't combine them. Intersection's looking only for the ones that are in both, right? If this was a union question, it'd be all the different numbers that show up in either one, right? But because it's an intersection, we're only looking for the ones that are shared in both, that are elements of both sets. So what are those? 2 and 4. Yeah, those are the ones. If you look, these are the ones that show up in both. And so the answer is the set 2, 4. Okay, make sense? Okay, you guys are good to go. I will stop. You may work.